Welcome, class. Today, we're going on an absolutely incredible inside-out journey in this explainer to discover the sheer natural forces that are continuously sculpting our dynamic planet. We walk outside, we see mountains, valleys, rivers, and it's super easy to think of them as these permanent, unchanging fixtures. But the truth? The Earth's surface isn't static at all. It is constantly, and I mean constantly, getting a massive makeover.
But before we really look at the landscapes we live on, we've got to start with one massive question. What powerful forces are actually shaping the Earth's surface in the first place? Well, to understand the gorgeous scenery around us, we have to realize there's this epic, ongoing battle happening right beneath our feet and right above our heads. We've got immense internal pressures pushing up from below, fighting against powerful external forces, scraping everything away from the top. To figure all that out, here is our roadmap. We're going to start deep in the Earth's hidden layers, move on out to the tectonic plates, explore weathering and erosion, follow rivers down to their deltas, check out some coastal and desert landforms, and finally, wrap up with how all these crazy landforms actually shape human life. Okay, Section 1, the Earth's hidden layers. Let's dive deep, literally deep, beneath our feet, and start from the inside out. The Earth isn't just one solid, boring ball of rock. It's actually built in distinct layers. Right there in the absolute center, you have the core, which is incredibly hot and incredibly heavy. Sitting right above that is the mantle, this super thick layer of rock. And here's the kicker. The intense heat from that core actually heats up the mantle above it, and that heat basically drives the entire geographical system of our whole planet. Finally, right on the very outside, you have the crust. That's the super thin layer where we all live. And when I say thin, I mean thin. As you can see in this breakdown, the crust varies from about 30 to 40 kilometers thick under our continents to just 5 to 7 kilometers thick under the oceans. Now, when you combine that crust with the rigid upper part of the mantle, you get a layer called the lithosphere. But here is the absolute secret to why the Earth changes so much. Did you know that sitting right beneath this rigid outer layer is the Asthenosphere? It's this incredibly hot, highly mobile layer of semi-molten rock. Which perfectly sets us up for Section 2, the moving tectonic plates. So because our crust is just sort of floating on top of that mobile, semi-molten layer, it isn't one perfectly solid piece. Think of it kind of like a cracked eggshell. It's broken into these massive slabs that we call tectonic plates, and fueled by convection currents, which is basically just hot rock rising and cooler rock sinking down in the mantle. These plates are constantly on the move, usually just a few centimeters a year. But when they meet at their boundaries, oh man, drama happens. They basically interact in three main ways. You have convergent boundaries where they crash right into each other, divergent boundaries where they pull apart and let new magma rise up, and transform boundaries where they aggressively slide past one another. And spoiler alert, that last one is a major cause of earthquakes. Time for a fun fact. Let's bring this a bit closer to home. Look no further than the majestic Himalayas. Have you ever actually wondered how they got so insanely tall? Well, they are a perfect real-world example of a convergent boundary in action. Basically, two continental plates collided, and the land had literally nowhere to go but up. So it folded and thrust into the sky over millions of years to create the highest mountain range on our planet. It's just a spectacular display of the Earth's internal forces at work. And get this, tectonic activity doesn't just build huge, snowy mountains. It can also create some wildly bizarre natural wonders. For example, did you know India actually has a mud volcano? Yeah, no joke. It's located in Baratang in the Andaman and Nicobar Islands. Down below, deep pressures literally force mud and natural gas all the way to the surface, creating these crazy, bubbling, muddy craters. How cool is that? All right, let's move on to Section 3, weathering and erosion processes. So we know internal forces push the land up, right? But what actually carves it into the shapes we see? The absolute crucial point here is understanding the difference between two external forces that get confused all the time, weathering and erosion. Weathering breaks rocks down right where they sit. It doesn't move them at all. This can happen physically, like from temperature changes, chemically from things like acid rain, or even biologically. Erosion, on the other hand, is the getaway car. It's the actual process where water, wind, ice, or waves pick up that broken down material and transport it miles away to an entirely different location. Just look at this drawing. This is biological weathering in action, and it perfectly shows how living things interact with geology. When strong plant roots force their way into tiny cracks just looking for a bit of water, they grow, They expand, and they generate this unbelievable physical pressure that can literally split a solid rock completely apart right exactly where it sits. Moving right along to Section 4, River Landscapes and Deltas. So once those rocks are completely broken down and carried away, running water steps in as the master sculptor. You can think of a river's life cycle like a giant, continuous assembly line of erosion and deposition that completely transforms the land. Up in its upper course, rushing super fast down steep mountains, it has massive erosive power, carving out deep V-shaped valleys and gorgeous waterfalls. Then, as it hits the flatter middle course, it loses a bit of that crazy energy and starts to meander or curve back and forth, creating features like oxbow lakes. Finally, it reaches the lower course. Here, it slows way down and just dumps all those rich sediments it's been carrying all the way from the mountains. And when that incredibly slow-moving river finally hits a static body of water, like a sea or an ocean, it drops absolutely everything it has left. Over time, all these dumped deposits build up to create this massive fan-shaped or triangular landform that we call a delta. And because this land is literally built from diverse, mineral-rich river sediments gathered from hundreds of miles away, the soil there is exceptionally fertile. Which leads us to a truly fantastic fun fact. Let's talk about India's famous Sundarbans Delta. Formed by mighty rivers flowing right into the Bay of Bengal, the Sundarbans uses these exact river deposits to create some of the richest alluvial soil on Earth. This makes it an absolute powerhouse for agriculture, perfectly suited for growing vital crops like rice and jute. It is the perfect example of how violent mountain erosion hundreds of miles away creates the very ground that feeds millions of people today. Okay, Section 5, Coastal and Desert Landforms. We've talked a lot about rivers, but they definitely aren't the only forces at work here. Out on the coast, you've got constant ocean waves undercutting the base of the land. I absolutely love this comparison because you can see exactly how it works. When powerful waves erode the weaker parts of a rocky headland from both sides, they eventually punch right through to meet in the middle, creating a hollow sea arch. And eventually, over time, the roof of that arch is going to collapse entirely, leaving behind just a tall, isolated pillar of rock that we call a stack. Meanwhile, if we travel to dry desert areas where water is super scarce, the wind takes over as the primary sculptor. And did you know you can tell exactly which way the wind is blowing just by looking at the shape of a sand dune? It's true. Barchan dunes take on a crescent shape from a single wind direction. Longitudinal dunes form these long, sweeping, parallel ridges. Star dunes, with all their multiple arms, pop up when the wind is blowing from a bunch of different directions at once. And then you have parabolic dunes, which are distinctively U-shaped. It's like a giant sandbox shaped entirely by the breeze. And finally, Section 6, Landforms and Human Life. Now, why does all of this matter to us? Well, all of these spectacular geographical features don't just exist in a vacuum. They directly, heavily influence human civilization. Throughout history, we have constantly had to adapt to this dynamic Earth. Think about it. Massive tectonic movements created the Himalayas, which then acted as this colossal natural wall, physically shielding India from northern invasions, while also creating massive cultural exchange choke points like the Khyber Pass. Meanwhile, the incredibly fertile plains and deltas carved by our rivers gave rise to the very earliest human cities and agriculture. The bays and sea arches created by coastal erosion provided safe, natural harbors which completely enabled global sea trade. Even the harshest deserts shaped human history by defining vital narrow travel paths like the famous Silk Road. So we've seen how internal heat drives the plates, how those plates build massive mountains, and how water and wind carve them all back down, basically building the very stage that human history is played on. As we wrap up this explainer on the incredible natural forces shaping our world, I really want to leave you with one final, provocative mystery from our planet's restless interior. With absolutely everything we know today about tectonic plates and fault lines, is it actually possible to predict earthquakes? It is a huge question, and one that scientists are literally still racing to answer today. Thank you so much for joining me on this deep dive into the awesome forces that shape our Earth.